So this is a piece of AuPt that I started working on about 4 years ago when I first found it. Actually, I found it a long time before that, but I didn't know it. And I've got a bunch of them, sitting around because I always thought they were interesting. Just didn't know why. So I cut this one in half to see what was inside. And it's pretty much the same inside as it is on the outside. As you can see, there's like lumps of gray stuff and lumps of gold stuff. And when you zoom in, it's more of the same. And this is not like, I don't have any lacquer on this or anything. This is a really old rock. And so what I did was polished it. And there you see the cubic structure. You can see the lines lining up in rows and columns. And they line up across the whole stone. Through the gold stuff, through the platinum stuff, and that's what it is. AuPt, gold platinum alloy. And this has like pictures in it. So that's my first kind of experiment with AuPt to see what it was. And you get this three-dimensional checkerboard at all scales. Gold, platinum, gold, platinum, gold, platinum. Because even if I zoom in on the gold stuff, it's made up of gold, platinum, gold, platinum, gold, platinum too. There's just more gold than there is platinum. It can be there's a 13 atom unit cell that has can be all one or all the other, all platinum or all gold, and anything in between. Anything in between. And that's why there's so much variety, because they're definitely different metals. They do not combine with each other like silver and copper, for instance, in excuse me, in sterling silver. You can't see the copper in sterling silver. Um, this stuff you can always see the separation between gold and platinum, because they're different metals. They're in a different family, and platinum group metals are different than gold group metals. They are attracted to each other because they create a north-south orientation. And that north-south orientation is carried out throughout the entire structure in a cubic way. And it's a three-dimensional checkerboard, but that means that the like all the red squares and all the black squares are not right on top of each other, with all red squares in one column and all black squares in they alternate in both directions, and up and down and sideways. And so you get a three-dimensional checkerboard in all directions of gold, platinum, gold, platinum, gold, platinum. And you can see as I move my stone around, it changes from kind of silvery blue to goldy silver. And that's what that is. Gold, platinum, gold, platinum, gold, platinum. So, and this came out of the Gila River up near, or over by Safford, Arizona. I live on the Gila River in west of Phoenix, Arizona. It flows from western New Mexico and the Rocky Mountains um, to the Colorado River, just above the entrance to the Gulf of Cortez, just before it goes into Mexico. And if you look at the end of the Colorado River there, the part that's in Mexico, all this stuff washed down, all that volcanic ash washed down the river, and it's now collected. There's a big, big area on the east side of the river that's just covered with gold-colored volcanic ash. It's probably one of the biggest pure deposits in North America. It collects wherever water flows because it's the heaviest thing around. It's heavier than lead. It's heavier than just about anything except uranium. Uranium is 19, has a specific gravity of 19. It's 19 times more dense than water. That's what it means. That's what the specific gravity means. 19 times. Uranium, right? That's the heaviest element in the 92 elements. Gold is also 19. has a specific gravity of 19. It's 19 times more dense than water. So a gram of water weighs, a cubic centimeter of water weighs 1 gram. A cubic centimeter of gold weighs 19.3 grams, I think. And the platinum is 21, a couple of notches, more dense than gold. It's harder than gold, and it forms deeper. The gold is pulled out as a vapor into the platinum. Platinum comes out of the melt first. And so we'll find pure metallic platinum in most of these bits and pieces I have here. Not all of it. This stuff is not pure metal. This is a covalent metal. And, hold on. So, what I'm looking at here, this is not like shined up with a lacquer spray like I do sometimes. This actually shined up like a piece of metal. And this is actually a ruby, rather largish ruby. But I wanted everybody to be able to see it because what you do when you're testing things is you test their hardness. Okay, so I just, put a scratch across there. And you can sort of see it. Not really. Really what happened was it's harder than my ruby, and it wore off some little pieces of my ruby. How about that? And that's really, truly AuPt, the real thing. Au is gold, Pt is platinum, and they join together with double covalent bonds, not metallic bonds, covalent bonds. So it doesn't pass electricity, right? Covalent bonds are exclusive of all else. And that's why the melting point is so high. The melting point is indicative of the amount of enthalpy it has. Enthalpy is the resistance to change. And then platinum has a tremendously high enthalpy. And AuPt, I think, has an even higher enthalpy because of the bonds between them. Although they may just share double covalent bonds. In the platinum itself, I know it does. Leaves red stuff behind. What does that tell you? It's harder than my ruby. Ruby is 9 on the Mohs scale of hardness. AuPt, diamond, and silicon carbide are the only things that I am aware of that are 10 on the Mohs scale of hardness. And if you look up the Mohs scale of hardness, it's Mohs'. Mohs. Somebody owns it, right? Mohs scale of hardness. It's a relative hardness with a scale from 1 to 10. And on most books and everything, they'll tell you that everything, right? That diamond is the only thing on the 10 part of that scale. They say that silicon carbide is 9.5, but they don't know, man. They don't know because they don't know enough chemistry to understand double covalent bonds, and they didn't test it with a hardness test because when I test silicon carbide, I in fact cannot scratch it with AuPt or a diamond. That means that they are exactly the same hardness. AuPt, silicon carbide, and diamond all share double covalent bonds. That's why I can't scratch it. That's why it's so damned hard to melt. That's also why it's a room temperature superconductor.